Hello, so my name is Michele Joyner. I'm going to be talking about the introduction to the course in this lecture and giving you an overview of what to expect from all of week 1 lectures. Okay, so my background is in applied mathematics. I have done a lot of research in different applications that involve mathematical modeling. So my approach to this course is going to be from a very applications perspective. Stochastic processes, stochastic modeling in general, has a lot of theory. There's a lot of theoretical stuff. I am teaching this course with the goal of eventually the students actually creating mathematical models, creating stochastic models. So this is really from an applications point of view. There will be some theory involved, but not as much as maybe in some other courses that you might take in stochastic processes. So MATLAB is my main programming language. When we create these stochastic models, we're going to also want to simulate, see what the models tell us. So we're going to have a computational tool. MATLAB will be that tool for us. And don't worry if you have not had MATLAB before. I will be giving a crash course in MATLAB during week 1. And from there, I will also be giving sample code that you're going to be able to use, that you're going to modify for the first assignments. And it won't be until the actual projects in which you're going to actually be doing individual programming. So before we talk about stochastic modeling, let's talk about modeling in general. So the kinds of things that we wanted to look at are, what exactly is mathematical modeling? What does it mean when we do mathematical modeling? When are mathematical models actually used? Why are they used? Why are they useful? And what are the different types of modeling? Okay, so we're going to start off with what is mathematical modeling. Basically, mathematical modeling is a way to take some kind of complex phenomena that is happening around you and simplifying it and describing it using mathematical equations. So we're normally going to talk about differential equations, maybe how something changes with respect to time. So we take something really complex, we simplify it, hoping that we get all the essential elements of whatever we want to describe, and create this model. So the model is never going to actually recreate what's happening in the world around us, but hopefully it'll be good enough to answer whatever goals we want to accomplish with this model. So once we have a model, we actually do some theoretical analysis, try to check to see if our model is good. We do computer simulations of the model to actually answer some questions. So then, once we create this model, we compare it to maybe data, or we talk with experts in the field about our model. We determine whether or not we think our model is good enough. We keep refining the model until it is, and then we're ready to use the model. So some of the ways that we might use the model is to test a hypothesis. So, for example, if you're modeling antibiotic resistance in a hospital, one of your hypotheses might be that if you introduce a new drug into the hospital, then it can help reduce antibiotic resistance within the hospital. So the first thing that you would have to do is actually create a model of how currently antibiotic resistance spreads in a hospital. And then you have to figure out where in the model to put this this hypothesis in. What would that new drug actually do? Where would it react in the model? What is it going to change in the model? And so then you simulate and figure out how much of a difference this drug might make. We can also use the drugs to determine some kind of course of action. So in the example of antibiotic resistance, you might think, okay, so the best course of action to reduce antibiotic resistance is to introduce this new drug. Somebody else might say, no, the best course of action is to make sure everybody's washing your hands. You have a 99% hand washing compliance rate. And actually, the best thing to do, according to all the models that have been created so far on antibiotic resistance, is to wash your hands. So when you see those dispensers in a hospital room, go ahead and use it, because that's the best way to not spread antibiotic resistance. These models can also help you to inform clinical or experimental trials. And so I'm going to give you one example in Lecture 2 where using a mathematical model you can actually inform a clinical trial, maybe how to administer a a new drug, when do I administer it in terms of when a person's sick? When do I actually administer this new drug? So it can help with clinical trials. So now we need to go to the question of the different types of models. So here, like I said before, what we're going to assume is that we have some kind of process that we want to model. And for now, for the sake of this lecture, we're going to assume that the process changes in time. Our process is x, and so t is our independent variable. So we're going to assume x changes with respect to time. And so now there's different ways of actually looking at how do we describe how x changes with respect to time. The deterministic approach says, well, if we're looking at x changing with respect to time, then we're looking at dx dt. Just from Calculus 1, dx dt describes how x changes with respect to time. And we're going to create some model f of xt, which takes into a bunch of different parameters and how x is going to change with respect to time. And so this is our deterministic approach. We come up with our model f. It's going to describe simplistically how x changes with respect to time. A non-deterministic approach is basically, here we have this deterministic part, this f of xt, but now we've added some non-deterministic term in it. So we don't have just the f of xt, we actually add some kind of stochasticity or randomness into it. Okay, so this is just a short introduction to the course. What I'll do in lecture 2 is actually focus on specific mathematical models. So I'm going to give you 5 different models in lecture 2 and show you why they're useful and give you an insight into actually deterministic models and stochastic models. So lecture 3 will take these 5 models and actually show you why one is considered deterministic, why one is considered stochastic. And then your first assignment will be this week, and it'll be actually taking some code, some MATLAB code, running the code, looking at the output of the code, and analyzing what a deterministic model will tell you versus what a stochastic model will tell you. So these are going to be corresponding codes for the exact same process. One's going to be deterministic, one's going to be stochastic. So I'll go over all the details of the assignment in lecture 5, but you really need to watch lectures 2 through 4 before watching lecture 5.